slackers in my life. So if the slackers want to do it. So I'm going to sit over here again. And hopefully I know that I'm doing it. All right. So we open up our book here and take a look at the most generic problems that run in there and fall into the category of what you're talking about, I think, is where you at? Oh, look, these are new. These are new problems. I didn't even know that. More door handle problems. We needed more door handle problems because really the only one that they had in here, I don't even see the old door handle problem. Wow, that's exciting. I know. Easily amused. Dr. Deal got there's the classic door handle problem right there. They use this one for like several problems, right? So they put the Fx, Fz, and Fy onto the thing, and then they have that point A, but you could also have like one onto the side and that kind of thing. And here's one of the other door handle problems, right? Between those, so, you know, like if you actually go through this book and through the other chapters, they refer back to these problems again for the other topic that they're going to do. So if you're just trying to review, like what are you covering in this book? Where you have that kind of problem, and they have all these 3D shafts, right? And then you look at some of the other, and there's not that many other problems. Now they have new door handle problems. These are cool. So we could do these, and maybe these are difficult problems. So do you want to do one of these? Sure. All right, so the first aspect that makes these difficult problems is finding the reactions. Doing the statics. So let's go for this guy right here. And then even before that is just trying to picture what this looks like in 3 different views. So let's try to do the good place to start. We like X and Y, right? X and Y is a good, those are good right there. So we want to try to sketch this thing in the XY plane. You know, and I'll even write in my book, I don't mind. In fact, I really like owning books so I can write in them. I didn't like that when you used to have to borrow books and get them back. There's the big I to look from the XY plane. So if you do struggle doing this, and not everybody does, I think if you played with Legos as a kid, you're able to visualize stuff in 3D. But if you only played video games, if you played video game Legos, it doesn't count because it does all the figuring out of what the 3 dimensions are, right? Your spatial visualization. This is my unproven theory. I would like to like put a test up against it, but I don't have the time. But it'd be a long study, but fun. Yeah. So we play with the Lego. I think maybe if I get another job, it'll be at the Legos. I mean, I don't know. But anyway, what we want to do is we'll write out our FBD. We'll declare it's an FBD. That just makes me feel good this is what I'm doing in FBD. And then I'll say, that is the direction that I'm going to go. That is what X is. And I can see from this one that X is the length of this thing, right? It's in the X, so I'm like, maybe I'll make a light drawing of the thing. And by the way, this is my section of interest right there at the wall. That's our whole goal there. And we can see we go through a distance here of like 55 millimeters. They said it was in millimeters until we get to that thing. So at some point, we'll make it that right there. That's the only part of that we'd be able to see from our big eye. Then we get to this spot right here. And then there's a little tab, like a little thing. Useless, but I'm putting it there because it looks pretty. And then we say, okay, how does that, do I see that force that's in the Y direction? Sure. It's everything in the Z. If anything's coming in the Z, that's going to be into the page. It's going to be into our coming right towards it. Look at that's messed up. Okay. So no, we would be able to see that, and it would look upwards to us. This is in the Y. 200 newtons. And then we come over here. Let's take a look at this guy. 300 newtons, and that's in the x direction. So that would be right there. So we go over here to the spot where we cut the thing off and go, oh, that's going to be, that's going to have a reaction. It's going to be coming downwards right there. We'll say that this is R, A. We really, I don't know what to, because I also want to maybe make a little point over here to call B, and maybe I'll put one on the back side that I'll call C, and I want to come down here in the bottom I call D. Because we could look at all of those, and I think if we look at all 4 of those points, when we get to the stresses, we can kind of now see the thing that we're going to cover in more detail in chapter 3. But it's worth like kind of looking at it right now if we're going to see a complete problem, to see the interactivity of the stresses with each other, of the different kinds of stresses, because they don't always add, sometimes they subtract. So we got to try to see those scenarios, and if you see all 4 of them, I think it will be helpful. All right, so that's one of the reactions in the y direction. I just didn't want to call it A, but I will for the time being. And then this is going to be RAX. And there's also going to be a moment right here because this is cantilevered. And that moment is going to be about the z-axis. And you can see that this guy right here is going to create, right? So because he's got a distance from the thing, we're going to take it about this point right here. We're going to rotate it about this point. And that's going to cause a moment. And here's the moment arm. It's going to be, I'll put it as millimeters, 55 millimeters, right? And that's going to be counterclockwise. Therefore, and this one's going to go right through the point, so it doesn't create a moment. So if this is going counterclockwise, this has to go clockwise and be called the moment at about the z-axis. And we could write this out, and maybe I should. I think I got lazy in class, and I wonder if that's going to come back to bite me. But we can write the reactions right here. We just say RAX plus 300 equals 0. RAX equals 300. No kidding. We kind of just, yeah, there's not much on there. But if we were going to be very conscientious engineers, as we should be, we'd say, okay, that one's going down, say RAY, and that's going to be plus 200 equals 0. So RAY is equal to 200 newtons downward. Oh, I fell off the edge. Guess maybe I can move it up, or is that going to be too small? Okay, cool. And but here's really the one that we really care about, because this one is simple in this case too. It's going to be, I'm just going to say RZ. I want to make some distinction between this general moment and the specific reaction that's right there. So this one's clockwise, so it's going to be negative MAZ plus 200 times my 55. But I want to be careful. I want to use Newton meters, right? So if I have kilonewtons and I have millimeters, hey, the kilo kills the milli, right? Don't worry about it. But here, let's go ahead and write it out. It's 0.055 meters equals 0. And did I not? I didn't bring my calculator? That's interesting. But I have my. I always try to get engineers sold on the Hewlett-Packard reverse Polish notation. Have you ever heard of reverse Polish notation? No. It's a different way. Hewlett-Packard's the only one that does it. And I had a professor in undergraduate that convinced me, and I got sold on it. And it's a superior way. It's difficult to convince people. It's just, you could take my word for it. It's better. And the idea here is if I need to multiply 200 by 0.055, instead of, I don't use equals. There's no equals button on here. I enter that, and then I go 0.055, and then I have two numbers that are in the stack. I multiply them by hitting that. It's very simple. It's the difference between writing 200 times 0.055 equals, and getting something compared to 200.055. Boom. This is reverse Polish notation. And where it really helps is when you have a very complicated thing. If you get used to the fact that there's these 4 numbers, you only see 2 of the numbers in the stack right now, but there's actually 2 more. And you hit this button, this little thing, you could roll down through where they are. It just works out nicely. It's hard to convince someone in a short amount of time that but I try to. I have yet to make a convert. One of these days I will. So that's 11 Newton meters. And I always keep it in scientific notation there because it just makes life a little easier. All right, so that's in one direction. Let's do the other 2. I'll try not to spend too much time on this, but let's go to YZ. So we're going to look down that axis right there. Can you see that? Okay. It's hard, from this angle right here, it doesn't look like it's like contrasting enough. So look, I'm going to see the front face of that thing. This is also an FBD, so we'll call that. And here's my axes. Y is that way, Z is that. It's going to see that, and then this guy's going to be behind it. So we're going to have 200 newtons coming up that way. The 300 is coming right at us, so we don't see it. And so we're going to have our reaction. It's going to show it's back over here, but for us it's right here. And it's going to be that same RAY. But now we also want to put in the reaction moment that's going to be right around here, even though this stuff is kind of in the foreground getting in our way. This distance right here is 60 millimeters. And so if this one's going, this 2 is also going counterclockwise, so this must be going clockwise. And we're going to call that the MAX, because it's going about the x-axis. So the sum of the moments about the x-axis equals 0. Counterclockwise is positive. Negative MAX plus 200 times 0.06. I can almost do this in my head. Equals 0. So MAX is equal to 12, right? And maybe I should have answered these over here with little arrows just to tell myself. And then lastly, let's see, we're going to do a top view. So that's going to be the XZ. And we'll make it that way and Z down. So looking down on it. So coming to there, and okay, so this force right here is coming up at us, so we don't see it. This one's coming right here, and that's going to be our 300 newtons. And the perpendicular distance there is going to be this guy, which appears to be 50. It's too bad they didn't put a force going in the Z direction anywhere. That would have been a little bit more helpful, but that's okay. Yeah, or just like another force put right there, right? Because that would make it more interesting. Yeah, so here we're going to have that same RAY x. And now this guy is going to operate, and he too is going counterclockwise. So this one's going to go clockwise, and he's going to go M-A-Y. Oh, and by the way, I should have probably said this is also the torque, right? This one up here. So the sum of the moments about the y-axis equals 0. And that means, let's see, our reaction is negative because it's clockwise. And then we're going to have, this is going to be counterclockwise, so that's going to be plus 300 times 0.05. Is that going to give me 15? Math. And just to be very nitpicky, I'm using 4 sig figs here. Obviously, it doesn't really matter, but it's just a good habit to really emphasize. You wouldn't believe how many people will just drop it down to 2 sig figs. Sometimes just drop it down to 1 sig fig. Sometimes really like, it's just too much hassle. Oh, I'm so tired of writing. I can't write more digits now. Okay, so we've got our loads figured out. Now, let's try for element A. We're going to do it, like I said, we're going to do A, B, C, and D. But we're just going to go down our list of possible things. So we'll start out in our list. Axial is one of the ones that we care about. So for axial stress, and this is going to be the stress, I guess, I'll do subscript for now, axial. F over A is axial stress. And we didn't actually know what the diameter, oh no, they told us there's a 12 millimeter diameter. So something I actually might do even before anything else, if I was doing this problem, and I should have done, I might actually go geometry, and I'm going to write it up here because it's a good thing to get out of the way. The area is pi over 4d squared, or pi over 4, 0.012 squared. That's one reason why I always use the, so we got 0.012, and then the square is that guy. And then I go pi times 4 divide, and I have 1.131 e minus 4, and those are meters squared. I'm really squishing things in here. And then I get I is pi over 64. Good thing to remember, d fourthed. I just wrote it again. 0.0124. It's not gonna be, I guess I'll put it right there underneath it, because all that got messed up. Okay, maybe I'll just erase this. There you go. I have an eraser. Can use it. 0.012 and a 4, and then there's this guy right there. Raise it to that, and then pi times, and then 64 divide. I think that's going to be right. 1.018. A lot of times when 1 is the first digit, it's almost better to go 5 sig figs. There's actually one in this Beard Johnston book right here. There's even at the beginning of the thing it tells you to do that. Oh, my name dropping. Dave Mazurek was the guy in the. He works at the Coast Guard Academy, and he was in my next door office mate at the Coast Guard Academy. And I sat through his mechanics and materials of book about 10 years ago, 12 years ago, something like that. Okay, cool. J, when it's a circle, is just 2 times I. So we can itty bitty shortcut there. It's nice to get those out of the way, so I'm doing. What's the question?
What are we solving for, or what is it?
Oh, you know, we really should have said that right there. Okay, so generally speaking, we're going to want to get, for this one, we're going to find the stresses on a stress element. Or in this case, okay, even better with the way they're phrasing it, we want to find the precise location of the critical stress element at the cross section at A. Like to find out like where is it going to fail? I mean, that's the problem. It makes sense. That's the thing we want to do. Now they're saying, they're actually saying A, I guess from this, they're inferring that it's all, like everywhere around the thing is section A, as opposed to saying element A. I kind of actually prefer that in one way. We could give the element another name or something or whatever. But we're going to try to find, first off, I want to find the stresses at this top, bottom, this side, and that side. Later on, what we're going to do is we're going to go, if there's a moment about the Z and a moment about the Y, we can vector sum them and find a magnitude that's some diagonal thing. And that's where the largest amount of bending stress is going to be. You know, actually, yeah. We'll find that it has a moment this way and a moment that way. So it's actually going to be, wait a minute, that way. So it's going to be a moment down that way, right? So it's actually going to be like a point that's like up here, that's going to be a tension, and a point down here that's going to be compression on a diagonal. But most of the time when we start out, the reason why I don't do that now is that just adds about 3 steps and a whole bunch of confusion to something that's already confusing students when it comes to trying to add transverse stress. Because the transverse stress is usually aligned with the, you know, when I'm doing elements that are on the corners.
Finding all the moments in X, Y, and Z to determine all the
Yes, yeah. So I'm just going through the process right here. Since we, like, if we had a problem, I would probably, in terms of the moment, not this one, but this moment and that moment, I would combine vector sum by going M max equals M a Z squared plus M a Y squared.
because the X is the torque.
Yeah, because it's the torque. Yeah, it doesn't do the thing. It only, all that one does, it doesn't do any bending. It just does twist. So for the force, we look at this, we see that the reaction at A is going to be the one that causes axial. So we see it goes 300 divided by the 1.131 E4. 1.131 E minus 4. And see, that's nice that it's in my stack still right there. I could do the little flipperoo thing here and take 300, and I cheat and I go divided, and then I hit 1 over because I'm really, really lazy. 2.653 E6, and oh, that's newtons per meter squared, I should point out, which means that's 2.653 megapascals. And then for bending, and by element A, I'm calling it the top right there. I start to look, and oh, and by the way, we got to make sure we mention this. That's tension, right? With a little T. We know that it's going to be pulling on the thing. For the bending, we know that's MC over I. And the moment to use for this one, and this is always like something we have to be a little bit careful of, it's either this one or that one, right? And so visualizing that can be a little difficult. Sometimes I think it's better, all right, so it doesn't really kind of look right because there is no stump right at the wall, but let's do it anyway. To look at that, this is the point we're about to look at, and to see which way these moments go. They're going to be the opposite of what we got up here, right? So here's the first one. This is about the Z-axis, and it's going clockwise. So this one goes counterclockwise. Does that make sense? So this is the MAZ. And the same thing here. This one is going clockwise here. So this one's going to go counterclockwise, which is going to be that way. The MAY. And you can just, you don't have to do this, but I think this helps. So now the big question is, which moment is going to cause the bending stress at that top element? It's either this one or that one. The MAZ, yes. And will it be tension or compression? Yes. And you have to kind of convince yourself that. The pool noodle really helps, right? You can see that you're coming this way, and you're going to push on the thing, right? You're coming up here. Now, you could do it on the free body diagram too. You don't have to do the stump, because look at the way the direction it's going there. You can see it's coming this way onto it, and it's pushing there too, right? I don't know whether it's worth drawing the stump, but now if you do it, if you can understand it both ways, you really understand it, right? Yeah, like how it's going to affect that element, right? On the stump, that thing's kind of coming, it's doing something. You know that it has a partner. I don't have two of them, but you know, it's trying to put in a moment onto there, right? As opposed to this one, but it's putting a moment onto there, right? It's one goes one direction, one goes the other, but they're both compression, either way that you're looking at it. So it's the MAZ, which turned out to be 11. And the C of this is going to be 0.006, right, millimeters, 6 millimeters. And the I we calculated up above as being 1.018 E minus 9. And lazy man doesn't want to do that, so that's going to be here. And they go 11 times 0.006 times divide over there. And I get 60, I get 6.484 E7. So that's 64.84 megapascals, and he's going to be compression. Now we go torsion. Tau, and I like TORQ for some reason. I don't know why I started doing that, but I did a while ago, so kind of stuck with it. Torque. Saved all of 2 letters, U and E. So we already said that the torque is going to be the moment about X. And we're about to get to the thing that you were originally asking for. So, you know, I know that's a long way around to get to answer your question here. And we're going to divide by that J, that 2.036 E minus 9. So now I have to actually put all this in there. 0.006 times and 2.036 E9, make it negative, divide. And I get 3.536 E7 newtons per meter squared, or 35.36 megapascals. And if we want to answer the question that you were talking about right here, note that on this view, it's going clockwise again. So in this view, it's going counterclockwise, right? So if we were to look down on the stress element at that top right here, noteworthy would be XZ. this torsion right here would be coming across the face right there. Can you picture that? And so all of its brothers are coming that way. So we call this the tau, we'll call it xz. I'm going to say transverse tau tran equals, it's a circle, so it's 4/3 v over a. And if you don't remember that, you can go to the section in the book. I really think it's a good idea to put tabs in these various things. That's just a, if you're like uncertain during an exam and you want to remember, I'm trying to see, okay, shear stresses for beams and bending. So it should be here, should be right, there it is right there. There's an explanation of it. It's good to read those things too, right? In addition to what I give you in the class. But right here is the summary of it. And as I said, almost if you're going to keep the book, you could put a little, arrow. That this graph represents the one meaning for a downward arrow across this thing, right? So the high stresses are to the side of that arrow. So the question becomes on here, what forces cause transverse stress at the top of this thing? And it's a trick question. There are none. So that's why I want to look at the other. Look at the sides of it instead. Because that 200 newtons, that will cause a transverse shear at this side and the other side. But nothing at the top or the bottom.
What kind of force, if you have to draw one on the segment, will cause one?
That one right there, in the Z direction. That's why I said it would be nice if they had put something in the Z direction. But now we just have to go 0. Boring. Well, we do have the thing where we go, we have tension due to axial, but we have compression due to bending. And it almost turns out, unless the thing was really, really, really squatty, that bending is quite often much larger than the axial. All right, it's hard to, I guess not that hard. I guess I could probably, well, if I make this one large, if I put a big force right here down the thing, then that doesn't cause any bending and would cause a lot of axial, right? To make it more of a competitor. But this is 64, and that's just 2.6, right? So in the x direction, the stress is going to be the axial minus the bending, or 2.653 minus my 64.84, and we know that we're going to get compression here. So actually, do I have this in the stack still? There you go. They're in the stack. So I just hit, lazy man just hit minus. And it's going to be a negative 62.19 megapascal. And I don't want to write compression if I put a negative. I want to rewrite the thing as 62.19 megapascals and then say compression. Because you get double negative, right? So the next thing we're going to do in the next class, we're not going to do it now. We're going to reacquaint ourselves with Moore's circle, right? So in the problem right here, they say sketch the stress element and determine the magnitudes and direction for all the stresses acting on it. So we did that for the top element. But then the next says sketch the Moore circle, which we'll do a refresher in the next class. So we don't necessarily need to do that right now. So if we were going to relabel a stress element instead, whoop, dummy. Sorry. Shouldn't call myself dumb. Not very nice. And then these are all going to be the correct ones right there. So this is, and it's a really good idea to make the X, label that right there, And then so we'll write that this is going to be 35.36 megapascals. And then this is going to be 62.19 megapascals. And we don't need to write compression because the arrow shows us that it's compression. Now, if we want to go on the bottom element, which I think I kind of labeled D, I never say, so we go element D. We have to kind of visualize that maybe, and it's easier to like go back to our stump and see. Well, we have to actually kind of decide which way we're looking at the thing. I think because we're going to be flipping it up and looking at the top. I mean, it's kind of an uncomfortable thing to be doing here. But now the Z is going to be coming up that way. In order to decide which way the, remember this is the X face, this is the X face right here. This torque is coming around and coming around down that way right there, which means that it's going to go in the negative Z direction, right, across that face. So we know it's going to be like that because we drew the axes on there. This isn't something I'd necessarily do in any problems in the class because people already get confused about looking at the top or looking from the side that's in the front, as opposed to trying to mess around with your brain and do it from the underside. I don't know if there's any benefit to that. But the thing in this case is that now the bending is going to be tension. And so now the stress in the X direction is going to be equal to the axial plus the bending, right? Which will be something like, well, I could just do the numbers here. I don't have to do it one step at a time, but just the 64.84 and the 653, add them together, and we get a 67.49 megapascals in tension, right? So that's going to be, that'll be one that like to look out for. That's going to be more than the one on the top. And it turns out we'll learn later in the semester, there's many materials that are stronger in compression than they are in tension. Cast iron, concrete, those kind of things. Which makes kind of sense. Like you can push hard on them and they won't break. But if you start to pull, they have like inside they have little gaps and little inclusions of carbon or whatever the hell, or iron, sorry, and you pull them apart. Now they're just not as strong as tension as compression. So sometimes you're on the lookout for the worst tension in certain materials. This will have the same shear as the other one because it too does not have any transverse. So we're fine with that with the 35.36 megapascals. But now if we want to go to element, call it B, I guess. And that's going to be on the side, and that's the one that's in the XY plane, that way. Now we have to look at that 200, right? So we go to the transverse on this. On that element is going to have 4/3 V over A, where V in this case is going to be that 200. And the area, we did at the very beginning. You can kind of see why maybe I make the case for why you do that in the beginning of a problem, is you kind of get it out of the way. Also, you get partial credit. I mean, if I didn't already give it to you, I usually give it to you in a test because it takes some time. But I mean, that mentality, get the low-hanging fruit out of the way. Don't leave the page blank. I can't emphasize that enough. I can't tell you how many people have not been successful in my class because they left problems blank on exams. It's just a test-taking strategy 101. Don't leave a blank piece of paper. You can't get partial credit if there's nothing on the page. And I meant to close the gap of something I said that could really come back to haunt me, because students sometimes just remember something. And if you say they don't finish it up, I said previously I've had right around 50% successful, which means 50% unsuccessful. And I got to tell you, I can't tell you how many of those people who were unsuccessful left blank things or didn't turn homework in. You know, they just, but also having had this Friday session or creating it in the semesters when I could, I had much better success overall. So that's one of the reasons why I'm having the session and hoping that more people will come by. I said that for the recording. I know, it's only the first week. After the first exam, we will see people come in. Because I repeat myself a lot. I say the same things over and over again in each course in each semester, so I can't remember if I said this, so you'll probably hear me repeat the thing. But you can't learn from reading a problem. Have I already said that? Yeah. But can't tell you how many people, that's all they'll do when they prepare for an exam. Read through it. Yep, I know how to do that. Yep, okay, yep. Oh yeah, understand it. Totally, I'm ready to go. Then they get a problem. I don't know how to go I don't know what to do next. And I try to help them during the exam too, by the way. Some people, I don't know, in terms of test taking 101, go see what you can get out of the instructor. If you're stuck in something, go ask. What's the worst they're going to do to you? Give you a dirty look, give a snide comment? I'm not gonna. But I see a lot of people. Yes?
So when you're looking at point B, you're looking at the 200 force because that's the only perpendicular force to it.
Yep.
So that's the only reason you really look at.
You kind of got, like if you look at that cross section and see that 200 is kind of sliding up onto the thing. So over to the side, it's going to do something. And as you're looking at it, you can see right here, it's going to be going upward across the face of that. All right, so that one is the tau trans. But now take a look at what the torque is doing. Let's go back to this guy right here. And he's going downwards. You picture that? So they're actually opposing each other. So they're going to partially cancel each other out. Not cancel each other out, but they're gonna work to make a smaller overall value. I didn't calculate the thing, so that's like 204 times 3 divided 1.113. Oh, no, 1.131 E4 minus divide, and that comes out to 2.358 megapascals. Right? So, and then this one is the tau torque. So what we end up finding here is the tau, and this would be tau that's in the XY plane. It's going to be tau torque minus tau tran. And so they end up being torsional shear was 35.36 minus what we just calculated of 2.358. So I'll just type it in, 35.36 and 2.358 minus, so they get 33.00 megapascals. And we know that it's going to be going downward here because the torque was bigger than the trans, right? So when we get to this part right here, we can go that way, that way. And this is going to have a different bending than the other. It's going to have the same axial, but the bending is going to be different because there's a different moment. MC over I still, but now the different moment And we could see, well, just by process of elimination, that it was going to be MAY. But now the question is MAY causing tension or compression at this side piece right here? It's going to be tension. You agree with that? Okay. Good. So we have MAY, which was a value of 15, and 0.006 divided by my 1.018 E minus 9. And sometimes just my brain, things jump into my head, so I think, you know, this would be a good thing to say. So I had never thought to say this, but maybe it's something to keep in mind as this is in your engineering classes. As you're doing homework, as you're preparing for a test, think about put yourself back into what that test would be like. What could you do during a test that you're doing now that could be making you more efficient? That could be like, remember, hey, I got to store this away. So when during the test, remember to do this. And think in those terms. So when you're at the exam, you could have a nice pace to the thing, but you could slow down just when you get to the spot where you know you've made mistakes before. Double check the thing, and by doing that, you could actually really kick some ass on the exam. And that might, for some people, be just like, oh, that's just a total obvious thing. I knew that already. But for somebody else, maybe this oh, okay, yeah, that's a good idea. To start thinking in those terms, like preparing for the exam way before the exam, right? Just to have that mentality. Yes. No, but I think that class starts in 15 or 20 minutes. Oh, it's not with me. No, it's another professor.
The UT building now over here, right? That's what I was told.
Oh, this is the UT building, right?
Okay.
Yes. So that's Dana. Yeah. I know it's confusing. A lot of times I get confused by it too. Sometimes I forget. So you're welcome. And okay, so we're going to add tension and tension with the axial. With the axial and bending. So in the sigma x, well, I was going to leave that for the thing right there. So over there, sigma x is going to be that 88.41 plus the, where we have it over 4, 2.653. 88.41, 2.653 plus, and we get 91.06 megapascals in tension. So if we were to label this one, 91.06 megapascals and 33.00 megapascals. And we're almost done here. I just think for completeness, I don't know, you could probably figure out where we're going. It's a little bit difficult because I want to go on this side to take a look at there. And you can see that now, because we have the force coming upwards onto this, and a lot of times I will label on there. Now they're going to agree with each other, right? The torque and the transverse agree with each other. And now this is going to be compression, though. Do you feel more comfortable with these? Yeah. And then doing it on your own really will cement other thing. Well, it's really important because, really when it comes down to this thing right there, and you can understand maybe when and I don't want to overcomplicate the thing, but if you have one way that they sometimes will write out a moment is to have an arrow with two heads on it, and then you just do that by way of, right? That represents the right-hand rule of the bending of the thing. And so for the stump over here, we have counterclockwise, and here we have counterclockwise. So We have that and that. So the vector sum of those is like that.
It makes sense, it's just a little bit more involved with.
Yeah, but the problem that I have now is that this is like, if that's true, this is where the tension is going to be. No, that's where the compression is going to be, excuse me. And this is where the tension is going to be. So if I have a stress element here or a stress element here, the transverse becomes, I mean, this is good to know right here. Transverse becomes a little bit more of a pain in the ass because you have to figure out, now you have to take that force that's in that direction and like break it down into components that are in that direction and that direction. You see what I mean? So I don't go there. Right? So put it out of your mind. But there is an example in Shigley where they do that. So just be on the lookout for that. And I think we got as much as we can out of this. Don't need to saturate it. There might be some repetitiveness as weeks go by, because there's some people that didn't show up that need this to be repeated and repeated and repeated, because they're not able to do this on the final exam. What we just did right here will be on the final exam in one form or another. And it's a necessary part of the thing. All right, so no, doesn't look like anybody showed up, but I'm gonna